Usually when we interact with our technology, there's this expectation of just absolute, undeniable precision.
Oh, yeah, for sure.
Like you look at a computer motherboard, you check a physical transistor, the meter shows 5 volts, and the engineer just points at it and says, yep, there it is, that is a 1.
Right, it's very cut and dry.
Exactly. But if you step into the architecture of a quantum computer, that precise little voltage meter completely breaks. Like we are forced into a mathematical landscape that is just fundamentally mind-bending.
I mean, it is the absolute definition of a reality-breaking paradigm shift.
It really is. And, welcome to the deep dive, everyone. Today, we aren't just going to marvel at quantum weirdness and call it a day. We are actually cracking open the mathematical tools, like the matrices, the complex vectors, the imaginary numbers that scientists use to calculate the seemingly impossible.
Yeah, we're really getting into the weeds on this one.
We are. So if you are that person who is constantly asking why and how, you are in the right place, we're going to start with the baseline of how classical logic handles uncertainty, break that reality with the double slit experiment, and then build a new mathematical vocabulary to understand qubits and entanglement.
And to appreciate just how radical that quantum math is, we really have to start by looking at how our current classical systems deal with uncertainty.
Right.
Because classical hardware is strictly binary.
Yeah.
Just electrical currents turning switches on or off. So it handles the unknown through standard probability and statistics.
Which is pretty straightforward.
Exactly. Think about a classic business logic scenario, like predicting customer behavior on an e-commerce site.
Oh, yeah. The sources outline a pretty standard funnel for this. Say you have a massive data set, and you know that historically 10% of visitors who view a specific product page will actually add that item to their cart.
Right. And then out of that specific group, 50% of the people who add the item to their cart will follow through and buy it. So in classical probability, to find the chance of a random visitor doing both of those things, you treat them as independent, mutually exclusive events. You just multiply the probabilities.
Right, so 10% times 50%.
Exactly, which gives you a 5% overall chance that a single new visitor will complete a purchase.
Okay, let's unpack this, because this is exactly where classical logic hits a wall for me.
How so?
Well, classical computing and classical probability is incredibly linear. It's like reading a book word by word, from left to right.
Yes, that's a good way to put it.
When a classical computer runs that e-commerce algorithm, it evaluates one user, calculates the 5%, then moves to the next user and the next. It evaluates the possibilities sequentially. We are basically just analyzing the past to guess what the next word in the book is going to be.
Yeah, you're locked into a single timeline of computation. If you want to evaluate a million different branching possibilities, your classical processor literally has to march down each path, one by one, just checking conditions.
But what if you could read the entire page at the exact same time instead of guessing the next word?
Oh, now you're talking.
Right. What if you didn't have to process possibilities one by one, but could evaluate every single path simultaneously?
Well, to read the whole page at once, we have to move completely past classical logic. We have to look at the actual fabric of subatomic reality.
Because things get weird down there.
Very weird.
Yeah.
Because the universe at its smallest level doesn't operate like a series of binary switches.
I am so ready for this. We are talking about the moment where classical reality literally breaks, which is the double slit experiment. The sources bring this up as the foundational proof that the universe is just weirder than we want it to be.
It really is. It's one of the most famous experiments in physics. It was originally conducted by Thomas Young with light, but later refined with lasers and single particles.
Okay, set the scene for us.
The setup is elegantly simple. You have a laser that fires tiny particles of light photons at a solid barrier. This barrier has 2 narrow parallel slits cut into it. And behind that barrier is a blank wall covered in photographic film to record where the photons hit.
Okay, so if photons are just physical particles, like, I don't know, tiny microscopic tennis balls, they should just fly through those 2 slits and leave 2 distinct vertical straight lines of marks on the back wall.
That's what you would expect, yeah. But they don't.
They don't.
No. When the laser is fired, the back wall doesn't show two lines, it shows an interference pattern.
Wait, what does that look like?
It's multiple alternating bands of bright light and dark shadows, just spread out across the entire wall.
Wait, an interference pattern. So the light is acting like a wave of water, like ripples in a pond going through two gaps where the ripples just crash into each other.
That is exactly what an interference pattern implies.
Yeah.
The wave of light passes through both slits simultaneously, splits into two waves, and those waves interact. Yeah, where the crests of the two waves meet, they amplify each other. That's constructive interference, creating the bright bands on the wall. And where a crest meets a trough, they cancel each other out. That's destructive interference, which creates the dark bands.
Okay, so light is a wave. That's cool, but I mean, that's not exactly reality breaking.
And scientists got the exact same thing. But they wanted to know the mechanics. They wanted to know exactly which slit each individual photon was traveling through to create this wave pattern.
Which makes sense.
So they placed a highly sensitive measuring device, an observer, basically right at the slits to detect the particles as they pass through.
And what happens when you try to measure a subatomic wave?
Well, the very act of observing the photon caused its wave function to collapse.
Collapse, just from looking at it.
Yes. The second they turned the measuring device on, the interference pattern in the back wall completely vanished.
You're kidding?
No. The photons stopped acting like overlapping waves and instantly started acting like regular physical tennis balls. They just left two straight lines on the wall.
Wow, the observer effect. Just by looking at the particle, we forced it to choose a definite state.
Exactly. It forced the photon out of a realm of probability and into a fixed physical reality. And when they turned the measuring device off, the interference pattern returned.
That is wild.
And it gets crazier. To eliminate the idea that different photons were just bouncing off each other, scientists slowed the laser down to fire just a single photon at a time.
One individual particle fired at the slits.
Right. And you would think one photon can't crash into itself, right?
Obviously.
But over time, as those single photons hit the back wall one by one, they still built up that exact same multiband interference pattern.
Meaning a single photon was somehow going through both slits at the same time, existing in a state of superposition and interfering with itself.
Yes. This is the core of quantum mechanics. Before measurement, a subatomic particle doesn't have a single defined location. It exists as a wave of probabilities. It is everywhere it could possibly be all at once.
Like Schrodinger's cat.
Exactly. If we tie this back to the sources, this is the reality behind Schrodinger's cat. The thought experiment where a cat in a box is simultaneously alive and dead until you open the box to check.
And this isn't just theoretical philosophy anymore, is it? The sources specifically mention how this exact wave function collapse is the foundation of modern quantum cryptography.
It is, yeah. Because the laws of physics guarantee that observation changes the state.
So how does that work for cryptography?
Well, if a bank encodes financial data into the quantum states of photons and sends them through a fiber optic cable, that data is physically unhackable.
Because if a hacker tries to intercept and observe that data midstream, the wave function collapses.
Exactly. The delicate interference pattern turns into random garbage data, and the receiving bank is instantly alerted that the line is compromised.
Because the data literally changes just by being looked at.
Right.
But wait, if a particle can be in two places at once, interfering with itself, how do you even write that down mathematically? I mean, a 1 and a 0 can't overlap on a spreadsheet. We need an entirely new mathematical language to map something that doesn't have a fixed state.
We do. And that language begins by abandoning the normal number line and utilizing complex numbers.
Okay.
To calculate these quantum probability waves, physicists rely heavily on imaginary numbers, specifically the concept of I, which represents the square root of -1.
Which, if you remember high school algebra, you can't do. You can't multiply a number by itself and get a negative result. -2 times -2 is a +4.
Right. It doesn't exist on a standard one-dimensional number line. But in quantum mechanics, we aren't dealing with straight lines. We are dealing with waves.
And waves are different.
Very. Waves have an amplitude, which is how tall they are, and a phase, which is where they are in their cycle. Imaginary numbers give us a mathematical dimension to map that hidden phase rotation.
Okay, I think I follow.
When you combine a real number with an imaginary number, for example, a plus bi, you get a complex number.
Got it. And the sources mention a process called finding the complex conjugate. Why are we manipulating these imaginary numbers if we eventually need a real-world answer to build a computer?
Well, because eventually we have to measure the quantum system. We have to extract a real physical probability from that imaginary wave state.
Right, the collapse.
Exactly. The complex conjugate is the tool for that. To find it, you just change the sign of the imaginary part.
Okay.
So if your quantum state involves a plus bi, its complex conjugate is a minus bi.
Oh, I see the algebra here. If you multiply them together, you are multiplying a plus bi times a minus bi. The middle terms cancel out, and because I times I equals -1, the I squared turns the negative into a positive.
Look at you. Yes, you're left with a squared plus b squared. All the imaginary components just vanish.
Wow.
This gives you what physicists call the squared magnitude, which is always a real positive number. That real number is the literal probability of finding the particle in a specific state when you finally measure it.
Here's where it gets really interesting, but also, a little heavy mathematically.
Yeah.
To organize all these complex numbers and probabilities, quantum mechanics uses matrices,
Yes.
which are tables of numbers organized into rows and columns. And you multiply them by taking the rows of the first matrix and multiplying them against the columns of the second. But why are we using accountant spreadsheet math for subatomic particles?
What's fascinating here is that matrices are not just static spreadsheets. If we connect this to the bigger picture, think about 3D computer graphics.
Okay, like a video game.
Exactly.
Yeah.
If you are playing a video game and you push a joystick to rotate your character, the computer doesn't recalculate every single pixel from scratch.
Oh, it just moves the whole thing.
Right. It takes the vector coordinates of your character and multiplies them by a transformation matrix.
So a matrix is an instruction set for movement. It mathematically rotates or shifts an object in space.
Precisely. In quantum computing, we use matrices to track and transform the probabilities of subatomic particles. We are literally rotating their probability waves.
Okay, that makes sense.
And different matrices do different things. An identity matrix, which has ones running diagonally and zeros everywhere else, is a do-nothing transformation.
So multiply a quantum state by an identity matrix, and it stays exactly the same.
Exactly.
The sources also highlight unitary matrices and Hermitian matrices.
Right, so a unitary matrix represents a reversible operation. In the quantum world, as long as you don't measure this system, it remains a fluid wave.
Fluid, got it.
So you can apply a unitary matrix to rotate a particle's probability, and then apply the inverse matrix to rotate it perfectly back to where it started. No information is lost.
Okay, but a Hermitian matrix is different.
Very different. A Hermitian matrix represents the actual act of measurement.
Oh, the observer effect again.
Yes. When you apply a Hermitian mathematical operation, it represents turning on that measuring device at the double slits. The math physically forces the complex probabilities to collapse into real numbers, which are called eigenvalues.
So it's an irreversible operation.
Completely. Once you measure the system and extract a physical 1 or 0, you destroy the superposition. You can't unmeasure it.
So the math literally mirrors the observer effect. That is wild. Okay, so we have the matrix math to map the movement. Let's look at how we actually map a single quantum bit, a qubit, using this math.
Let's do it.
Because a classical bit is a 0 or 1. But a qubit is represented by a state vector, which is a column matrix containing those complex numbers we just talked about.
And, writing out giant grids of matrices every time you want to do an equation gets incredibly tedious. So physicist Paul Dirac created what is known as Bra-ket notation. It's essentially a shorthand for matrix algebra.
I really love how visual this is in the sources. Instead of drawing out a matrix grid, we use little brackets. The state for 0 is called ket 0. It's written with a straight vertical line, a 0, and an angled right bracket. It represents a 2-row column vector of 1 and 0. In physical hardware, this might be an electron trapped in a magnetic field with a property called spin down.
Exactly. And ket 1 is the vector of 0 and 1, representing spin up. But the vital concept to grasp is what the numbers inside that vector actually mean. They aren't definite physical positions.
They're probabilities, right?
They are probability amplitudes.
Right, because before we measure it with a Hermitian matrix, it's just a wave of possibilities.
Exactly. The top number is the amplitude for finding the qubit in the 0 state, and the bottom number is the amplitude for the 1 state.
Okay.
If you calculate their squared magnitudes, using that complex conjugate trick from earlier, the two results will always add up to exactly 1, representing 100%. A qubit holds the mathematical probability of being a 1 and the probability of being a 0 simultaneously.
Okay, so a classical bit is a light switch, up or down, on or off. But a qubit is like a coin spinning in midair. While it's spinning, it's a blur. It is in a state of superposition, a mixture of heads and tails.
That's a great analogy.
Thanks. And the Bra-ket matrix math is just tracking the complex rotation of that coin. It tells us the precise odds of how it will land when we finally slap it down on the table to measure it.
The math maps the spin, exactly.
Mm-hmm.
But this raises an important question.
Okay, what is it?
Mapping one spinning coin is a neat trick, but a single qubit isn't going to revolutionize the global economy. If a classical computer can process 64 bits at once, how do we link multiple spinning qubits together to actually outcalculate a classical supercomputer?
Which brings us to what Einstein famously dismissed as spooky action at a distance: quantum entanglement.
Yes, entanglement.
The sources try to explain this with an analogy. They say, imagine you have one apple and one banana, and someone puts them in two separate closed boxes.
I know this one.
Yeah, so you take one box, I take the other, and we travel to opposite sides of the planet. The very second I open my box and see an apple, I instantly know with 100% certainty that your box has the banana. The state of one defines the other without any communication.
Right. It's a very common analogy, but we actually have to push back on it heavily.
Oh, really?
Yeah, that analogy represents what classical physicists, including Einstein, actually wanted to believe. Einstein thought the particles were like the apple and the banana, that they already had a hidden, fixed identity inside the box, and we just didn't know what it was until we opened it.
He called it hidden variables, right?
Yes, hidden variables.
Wait, so the apple and banana analogy is completely wrong.
Completely wrong. In the 1960s, a physicist named John Bell proved mathematically that there are no hidden variables.
But what's actually in the box?
In quantum entanglement, the fruit doesn't exist inside the box. Before you open it, both boxes contain a spinning, undefined superposition of both appleness and banananess.
Oh man, my brain is starting to hurt.
It is so counterintuitive. What entanglement actually means is that the two spinning coins become mathematically locked together into a single shared state.
Okay.
The second you open your box, the universe instantly spawns an apple, and that measurement physically forces the other box, even if it's on the other side of the galaxy, to instantly collapse its superposition and spawn a banana. The particles are literally communicating their collapsed state to each other faster than the speed of light.
Okay, so if they are locked together into a single shared state, how do we track that massive shared state on our mathematical spreadsheet?
We use the final piece of the puzzle, which is tensor products.
Tensor products?
Yes. A tensor product is a specific way of multiplying two matrices together to combine two separate quantum systems into one larger system.
How does that differ from the regular matrix multiplication we talked about earlier?
Well, in classical physics, if you add a new component to a system, you just add their properties together. The math grows linearly.
Right.
But a tensor product multiplies the entire dimensional space of the matrices.
What does that mean in practice?
If you have one qubit, it has two dimensions of probability. If you introduce a second entangled qubit, you don't add 2 plus 2. You multiply the dimensions. You take every single element of the first qubit's matrix and multiply it by the entire matrix of the second qubit.
So a 2-qubit system has 4 dimensions of probability. It maps the state of 0, 0, 0, 1, 1, 0, and 1, 1 all simultaneously.
Yes. And add a third qubit, and the tensor product multiplies the dimensional space again. Now you have an 8-dimensional matrix. It grows exponentially. This is why quantum computers are so powerful.
So what does this all mean? Let's bring it all full circle back to our original problem with the classical e-commerce algorithm. We said 8 classical bits can represent exactly one single number between 0 and 256.
Right, because a classical system is just 8 physical switches locked into a specific on or off pattern.
But an 8-qubit system, mapped together using tensor products, doesn't hold one number. Because the qubits are in superposition blurring heads and tails and entangled together into a massive dimensional space, those 8 qubits hold all 256 possibilities simultaneously.
By applying unitary matrices, a quantum programmer can gently rotate the probabilities of all 256 paths at the exact same time.
Wow.
They use constructive interference to amplify the probability of the correct answer and destructive interference to cancel out the wrong answers.
So it reads the whole book page at once.
Yes.
We aren't just calculating faster, we're actually computing across parallel realities.
Basically.
By manipulating these massive probability matrices with complex numbers, a quantum computer processes millions of branches in a single mathematical instant and then we measure it, collapsing the wave function to spit out the optimal path.
That is the magic of quantum computation right there.
Okay, let's quickly recap this journey. We started with the simple, rigid binary limits of classical computers, evaluating logic one step at a time.
Right.
Then we broke reality by looking at how photons can interfere with themselves and exist in two places at once in the double slit experiment. Finally, we learned how complex numbers map the hidden phases of these waves, how Hermitian matrices map the irreversible observer effect, and how tensor products allow us to entangle qubits into an exponentially massive space of simultaneous calculation.
And the reason you should care about this is profound. This math is no longer confined to chalkboard theory. Companies and governments are physically building these machines right now.
Yeah, it's really happening.
Whether it's creating unhackable cryptography or simulating complex molecular structures to discover new life-saving drugs, or even optimizing global supply chains, understanding this dimensional math gives you a glimpse into the actual engine of the next technological revolution.
It is the literal blueprint for our future. But before we wrap up this deep dive, I want to leave you with a final, slightly provocative thought based on the physics we just unpacked.
I love these.
We just learned about the observer effect, that the wave function of a quantum particle exists as a fluid blur of probability, and it only collapses into a fixed physical state when it is measured or observed.
Right.
But if everything in our macroscopic universe, the device in your hand, the trees outside, the distant stars, and your own body, is ultimately made of these exact same subatomic particles,
Yeah.
does our reality only have a fixed shape because we are constantly interacting with it?
Ooh.
When you leave a room and shut the door behind you, does the room revert to a matrix of mathematical probability? What happens to the universe when absolutely no one is watching?
Yeah, that's a wild thought.
Think back to that clean, comforting voltage meter pointing at a 1 or a 0. We desperately want things to be certain, but maybe the certainty only exists because we demand to see it. Thanks for exploring the math behind the madness with us. Keep questioning everything.